Hi, good afternoon, everyone, and thank you for joining us. I'm Naomi Gonzalez, the Education and Interpretation Specialist at the Science History Institute, and I'd like to welcome you to our Lunchtime Lecture Series. Now combined with the Saturday Speaker Series, our lunchtime lectures take a rigorous and entertaining approach to exploring topics for scholars and anyone interested in stories about the history of science. This season, our speakers are exploring issues of gender, race, and colonialism in the history of the physical and biological sciences from the early modern period to the 21st century. Today is our very first in this season, so our first speaker that's kicking us off today is going to be Roger Turner, a research curator at the Science History Institute. Roger is a historian and storyteller. His particular scholarly expertise is in 20th century atmospheric science, scientific instruments, and environmental monitoring. At the Science History Institute, Roger has helped to launch the student role-playing game Science Matters, the case of rare earth elements. He's worked on the film The Instrumental Chemist, which is available for watching and streaming currently. He developed the playful online experience Instruments of Change, and he contributes to museum exhibits. He also occasionally writes stories for our Distillations online magazine. Before coming to the Institute, Roger taught at colleges and worked as a public history consultant, advising on oral history preservation, collections development, and public communications. His research on weather forecasting has been funded by the National Science Foundation, the American Meteorological Society, and the Smithsonian National Air and Space Museum. You can read the bits with neat pictures at picturingmeteorology.com. Today, Roger will be discussing how we can revise science stories to be more inclusive by looking at two instruments currently on display at the Science History Institute. Bruce Merrifield's automated peptide synthesizer and John Fens' electrospray ionization mass spectrometer. So take it away, Roger.
Thanks, Naomi. Delighted to be here to kick off our new series. I'm here in my wife's office at Dickinson College in Carlisle, Pennsylvania. So far from Philadelphia. But since this is a museum talk, I thought you'd really appreciate getting a chance to actually go inside the museum, at least virtually. So what I'm going to start off with is take advantage of the wonders of webcasting and start things off with my handsome colleague in Philadelphia. Thanks, Roger. I'm here in the museum at the Science History Institute, where we're currently installing the new interpretation of our main exhibit. Behind me is a Nobel Prize. Well, a replica, actually. We've been borrowing it from SUNY Stony Brook for the last few years, and it's just about to go off exhibit. But if there's just one thing that people know about science, it's that the Nobel Prize is the ultimate recognition of scientific accomplishment. It's like the Oscars of science, or what scientists dream of instead of winning the Super Bowl. But the iconic status of the Nobel Prize might be the only way that many people ever encounter basic research in chemistry, physics, or the life sciences. Unfortunately, the image of science projected by the Nobel Prize is wrong. It's deeply unrepresentative of how contemporary science actually works. So let's go beyond the Nobel Prize to see what's really behind two celebrated discoveries in 20th century science. Here at the museum, we exhibit two instruments that led to Nobel Prizes. This is the automated peptide synthesizer. This instrument was first imagined in 1959. During the 1960s and beyond, the instrument made it possible to synthesize in the lab all kinds of peptides and proteins, molecules that are crucial to our physiology. Bruce Merrifield was honored for his work in creating it with the 1984 Nobel Prize in Chemistry. And this is the electrospray ionization mass spectrometer. The instrument was developed and refined during the 1980s. It enabled scientists to identify unknown proteins, helping them to understand the links between the genetic code and the functioning of cells. John Fenn won a share of the 2002 Nobel Prize in Chemistry for his work with this instrument. Now, the two individual men recognized by these prizes were certainly scientific leaders, but they did not achieve alone. These instruments emerged from academic laboratories that employed women and men in a variety of roles. They were supported by families and communities, And beyond those labs were universities, generous government funding, immigration policies, and broader changes in technology that made possible advances in science and medicine during the second half of the 20th century. That's the bigger story that we're trying to tell here at the Science History Institute. So how does that more accurate and more inclusive story about modern science look like in detail? I'll send you back to Carlisle for that.
Thanks, Roger. So I want to walk you through this process of how we have reinterpreted our museum, or at least a particular exhibits in our museum, and how that's helped us to reach new audiences and help those audiences to see themselves in science in hopefully a more productive and engaging way. So our museum first opened in 2008. And the permanent gallery, which you see a photo of it here from 2008, was an exhibit titled Making Modernity. And it's built around hundreds of objects that would, as we put it back then, embody the story of the great human adventure of discovery in the chemical and molecular sciences. And what we told there was very much a tale of progress. But it was oriented to a particular audience. And that was an audience of people who worked in science, especially scientists and managers of chemical companies. As you may know, back then we were called the Chemical Heritage Foundation. And the historical collections that were central to our library and archives and the endowment that kept our institution going had largely been built with the support of people within the chemical industry and of the support of notable chemists. So our exhibit, Making Modernity, was meant to give these audiences a sense of the history of their work, a sense of connection to their past, and a sense of how chemistry was important in creating the world in which we live in today. But a funny thing happened in the years since the museum opened. For one thing, the museum has resonated with a rather wider range of audiences than it was initially intended for. We do get retired scientists and executives from Dow and DuPont and the pharmaceutical industry coming through. But we also get new audiences that we really didn't expect. For one thing, we get people who wander down the block with an hour or two to kill before their timed ticket to Independence Hall will let them in. We get high school chemistry teachers who bring their classes. We get fans of the All Souls trilogy, right? This wonderful, big-selling, best-selling series of novels about alchemy and early modern science and vampires, written by the historian of science, Deborah Harkness. And we also get what we call the science-curious public, right? This is people who are interested in better understanding how science and technology and medicine have shaped the world that they live in, for good and for bad. And a lot of people that come to our museum come in after they've attended one of our programs when we used to do these things in person, and so that's really kind of expanded the way that we've had to think about audiences and think about what we need to communicate to those audiences. So a few years ago, we started thinking about how we could change our permanent exhibit to better save this range of audiences that we attract. And given limited resources, the decision was made to refresh our galleries rather than remake our permanent gallery. We would keep most of the heavy objects in place. We would retain those, that kind of shiny blue, these expensive etched glass signs that introduced each main display, what museum professionals call the primary texts. So those had to stay. But what we would change would be the stories that we told about those objects. We were going to try and bring in more pictures of people. We were going to try and show a wider range of people. We try to include the groups of people who worked in science but whose contributions were marginalized or ignored or forgotten. And we try to talk more about things like pollution and protest and the ways that people have pushed back against the harms that have been caused by the making of modernity. In short, we wanted to help our diverse audiences see more of themselves in science's past. So one of the pieces that was assigned to me for the refresh was a display called Soul of an Instrument. It's supposed to explain what historians of chemistry have called the instrumentation revolution. During the 1950s, sort of beginning in the 1930s, and really kind of reaching, really starting to flourish in the 1950s, the chemistry lab was beginning to, as we put it on one of those blue signs, fill with electronic instruments that enabled completely new types of synthesis and analysis. And basically, these are instruments that changed what day-to-day work was like in the laboratory. So one of those instruments that is featured is the automated peptide synthesizer, which led, as I mentioned earlier, the other me, to the award of the 1984 Nobel Prize in Chemistry to Bruce Merrifield. So back in 2008, we told a story that really focused on Bruce Merrifield's process of creating the instrument, right? How did this instrument come to be? We talked about how he came up with the idea in 1956, how he experimented for 3 years with different anchors and reagents and solvents to make the process work. Our signs explained how automated processes were much faster and reduced the quote-unquote drudgery of lab work. Now, to be sure, we weren't telling a completely heroic story of progress. We also talked about how the people who ran the automated machines lost their kind of visceral understanding of how chemical reactions work, something that came out of the previous sort of iteration of wet chemistry. And we certainly had a quote from Merrifield acknowledging how much of a debt he owed to his laboratory technicians. In short, what we had was the story of what it was like to work in science from the point of view of a celebrated principal investigator who runs his own lab. But, well, here's what Bruce Merrifield's research group actually looked like at 2 points on his way to the Nobel Prize. So on the left is a picture of his lab group from his research group in 1971. And on the right is his research group on the day that he found out about winning the Nobel Prize in early October, perhaps, let's see, exactly 36 years ago, perhaps today, in 1984. Now, Merrifield alone got the Nobel Prize, but look at how many people he had helping him. At least 6 of those people are women, and they're of different ages and different races. How did they contribute? What was their work like? So I started reading about Bruce Merrifield, and it soon became clear that he and his wife, Libby, were absolutely beloved figures in the international peptide community. That's Libby there on the picture on the right with her hand on the young woman who's wearing a sweatshirt, on the shoulder of the young woman wearing a sweatshirt. So nearly everyone who was anyone in the peptide research had spent time in the Merrifield lab or had learned from someone else who had been there. The people in the lab almost always ate lunch together. Every fall, they went to Bruce and Libby's home for a picnic where they remembered these intense games of volleyball and good-hearted leaf raking contests. And there's just sort of this sense of delight in the experience of being part of this lab. And Bruce Merrifield talked about how he had 2 families, is how he described it. His research group on one hand and his wife and children on the other. And postdocs and graduate students remembered Bruce and Libby really as almost surrogate parents, people whose, quote, advice on matters of the heart and soul was as good as any best friend, unquote, as one of those graduate students wrote in a remembrance some years later. And as it turns out, Libby was a biochemist as well. She was studying biochemistry at UCLA in 1944 when she met Bruce, who was her graduate teaching assistant at the time. Libby had begun a doctoral thesis when they married in 1949, but she stepped away from lab work when their first daughter was born in 1952, so she never did finish her PhD. But she returned to the lab in 1979, 27 years later, after raising 6 kids and enabling Bruce to spend evenings and weekends at work. And what did she do when she came back into a chemistry lab? Well, she took on the challenge of synthesizing human interferon, which is an antiviral protein. And Bruce considered this project too large, too risky, and too uncertain a project to assign to a postdoc. Libby actually went on to work in the lab until she was 82. So Libby's presence in the lab was also important for the technicians who dealt with hazardous substances daily, as they prepared samples and operated instruments while following protocols developed by other researchers. One of those technicians was Lucy Eskeland, the young woman in the sweatshirt in the front row. She worked as a technician in the Merrifield lab in the mid-1980s before going back to school for her own PhD. One day, she spilled dimethylfuramide, a common solvent that was used in peptide research. As Lucy remembered it later, Libby quickly took me to the shower. My toes shriveled like prunes, and my clothes felt like cardboard. So, in our new refreshed exhibit, you'll be able to see pictures of the women and men who worked in the lab. We show that portrait of Libby, as well as a group portrait of one of these from these backyard picnics that includes lots of children and spouses. And one of the things that we realized that we needed to do as we were reinterpreting these exhibits is we had to assume and start from a different baseline of knowledge, right? We couldn't assume that everybody coming to our museum already had a pretty good idea about how science, or at least how contemporary recent science works. So one of the things that we do in the new exhibit is we're quite explicit about the social structures that organize contemporary academic laboratories. So we explain how an established professor leads a team of scientists in training, which might include postdoctoral fellows, graduate students, even undergraduates, as well as technicians. We explain how the head of the lab's job is to secure funding and recruit staff and oversee the publication of results, while it's the postdocs and the graduate students who do much of the bench work, as well as the drafting of experimental protocols. They might even design and build new instruments, as we show. So a successful principal investigator needs also to recruit internationally to find just the right combination of skills that the lab needs to answer specific questions. So in our new refreshed interpretation, while the principal investigators remain central characters in our story, these Nobel laureates are just one of many people involved in doing the work of contemporary science. And we're trying to highlight the different kinds of labor that are necessary to make this transformative science. Science is synthesizing chemicals and running experiments and publishing papers, absolutely. But science also requires emotional labor and reproductive labor as well. Science is also building research communities. It's advising young people who are who are on their own, far from home, maybe feeling lost, not sure how to become a scientist. Right? It's that kind of work. It's also keeping laborers safe under potentially dangerous conditions, as we saw from Libby's assistance with for when Lucy Eskeland spilled the dimethylfuramide. Excuse me. And we're also trying to quietly show that getting a Nobel Prize and having a family at the same time required a stay-at-home spouse who was willing to pause her own career for decades, at least in 1984. Now, I was rewriting this exhibit as the Trump administration implemented radical changes in US immigration policy and proposed big changes in how science was funded and controlled by the federal government. And as I was thinking about how to refresh this exhibit, I saw a way to think about and talk about the many things that are outside of laboratories, as well as just laboratory work, that were essential to advances in science and medicine during the 20th century. So now I want to turn to the electrospray ionization mass spectrometer. This became an important tool in pharmaceutical and biomedical research in the 1990s, and John Fens received a share of the Nobel Prize in 2002 for his work with it. But Fens' long and winding career reveals how Nobel-worthy science is not a story of lone geniuses, but instead a story of connections, of exchanges, and of government policies. So as the United States became a hotbed for biochemical research in the decades after World War II, there were some really important external factors that mattered here. Abundant research funding, prestigious institutions, and relatively open immigration policies. So let's follow the career of John Fens a little bit. In 1952, the industrial chemist John Fenn, who was also trained as an engineer, became the project director of Project Squid, which was a project funded by the Office of Naval Research to assist in the development of jet-propelled cruise missiles that would be launched from submarines. And so this was actually the very first one was the JB-2 Loon, which is here being launched from a U.S. World War II surplus submarine. And aerospace historians will note that this is basically an American copy of the German V-1 buzz bomb that was used during World War II. And so the Navy was interested in basically developing better jet engines, but also developing a science base that could support the development of those jet engines. And so by funding pure and applied research at more than a dozen academic labs, the Navy sought to interest academic researchers in fields relevant to jet propulsion, including combustion, fluid flow, heat transfer, right? This kind of fundamental science, but that could be used and relevant to technological development. Starting during World War II, as many historians have noted, the Defense Department contributed lots of money, even for basic research on topics that were seemingly far from weapons. And as scientists and military funders exchanged ideas during the Cold War, each group uncovered new possibilities. This is what historian Paul Edwards has called a process of mutual orientation. And it changed both what scientists studied and how wars were fought. Now I'm going to come to my absolute favorite document that I've ever found on the history of 20th century science. And as I was researching Fens, the history of Fens' federal support and the funding for his science, I discovered in our records here at the Science History Institute a document, a file that Fenn called his humor file, and it's full of cartoons and silly signs and other bits of humor. But I think this parody of Psalm 23 is really my favorite. So I'm going to read it. I'm going to read it to you here. The government is my sponsor, I shall not want. He maketh me to rest in fine laboratories. He leadeth me into new facilities. He restoreth my over-expenditure. He leadeth me into the paths of classification for his security's sake. Yea, though I walk through the valley of the shadow of non-support, I will fear no contract termination, for thou art with me, and thou must spend all of thy appropriation. Thy funds and thy budget comfort me. Thou preparest a contract before me in the presence of my problem statements. Thou anointest my project with government-furnished equipment. My supply rooms runneth over. Surely a high overhead allowance and lenient cost inspectors shall follow me all the days of my research, and I will dwell in the favor of Congress forever. So I think you could this poem just sort of perfectly captures why so many principal investigators who led labs during the 1950s and the 1960s saw that as a time sort of for a golden age of science. And I think for scientists reading it now, that one certainly who are one part of our audience at the museum, this will be a really jarring and sort of remarkable contrast to the struggles that so many PIs have now, and so many young scientists have now as they try and launch their careers and find support for research. But again, it's a reminder of just how much of advances in 20th century science depended on the choices of governments and their governments and the United States federal government willingness to pay for and support institutions that made this science possible. So Fenn's own research during the 1960s and 1970s explored what he called molecular beams. Essentially, his research group had created the world's smallest jet engine, and it was able to direct individual molecules at a target to study combustion under incredibly controlled conditions. But this was work that depended on immigration and international exchanges, as well as a cooperative work environment that we can see here in the illustrated in some of the pictures that came out of John Fenn's lab. So in 1980, a colleague of Fens from the Yale Medical School showed Fen a paper that had cited Fen's work, and which had suggested that large organic molecules could be separated by spraying them from an electrically charged needle. The electrospray system essentially was a way to study, to analyze and identify proteins. It would become that. But the actual electrospray system was first built by Japanese postdoc named Masamichi Yamashita, who was on leave from Japan's Institute of Space and Aeronautical Science, and it was the heading of his stationery, actually, that had the newt on it that I was showing you a little bit earlier. He later became sort of famous as a person who sent newts into space to study some physiological effects of zero gravity. But at the time, he was a postdoc with an amazing mechanical talent, and he scrounged from obsolete equipment around Fen's lab to build this first electrospray detector. He really was the person who made the instrument a mechanical reality. After that, graduate student Craig Whitehouse built a housing for a more sensitive detector, which was a quadrupole mass spectrometer that had actually been loaned by a commercial instrument company. For a while, Craig Whitehouse was, as John Fen groused, quote, the only one who knows how to use or run the spectrometer in the entire lab. So again, this sort of illustration that the principal investigator is managing and guiding the work of this lab, but doesn't actually do the day-to-day bench work, or doesn't actually even know how to operate these key instruments. So this new upgraded instrument with a quadrupole mass spec could produce what Fen described as beautiful spectra of peptides. But moving up to larger protein molecules required a signal processing algorithm that was written by Matthias Mann, who was a graduate student that Fen had recruited from Germany. So what we can see is that the development of the electrospray ionization mass spectrometer was an international effort, requiring many people. It depended upon contributions from people born in the United States' former enemies, who were attracted to come to the United States by strong institutions supported by abundant government funding for science. But of course, only John Fen was recognized with the Nobel Prize. So to come back to my opening point, and I'll close here, the Nobel Prize, I think, gives us a useful but quite distorted view of modern science. As we've seen, this week with the Nobel Prizes, when a Nobel Prize is awarded, it's one of the few moments when media, all kinds of media, the television news, newspapers, websites, even Twitter and maybe Facebook, are talking about basic research, right? The sort of fundamental research that is the building block of modern science. It's one of the few times when people actually kind of encounter that. And because of that, it makes for a really nice opening, a nice opening for engaging with audiences, right? When you tell an audience this is research that led to a Nobel Prize, they at least have a hook, something that they know they can go, oh, okay, this is important work. But as we know, the Nobel Prize, the rules of the Nobel Prize say that only 1 to 3 people can get the prize, and it's only for something defined as a sort of a discrete moment of discovery, right? And so these problems with the prize, I think, really mislead the public about how modern science actually works. So I hope that gives you a sense of how we're trying to make a rather abstruse museum display more inclusive and more engaging for an increasingly heterogeneous groups of visitors who come to our museum. And I look forward to hearing your questions and engaging with you by text and in our conversation.
That was great. Thank you so much, Roger. So I will remind our audiences, we do realize we've had a little bit of technical difficulties with our chat feature on YouTube. So if you do have any questions for Roger, you can email us at education at sciencehistory.org. So please feel free to shoot us your questions and your comments. We will be checking them, and we will make sure that this issue is fixed for our lecture next week. So while we wait for questions, I actually very quickly wrote a couple down that hopefully make sense. Your talk was really great, and I think, and you mentioned the Nobel Prize just recently being announced this week, and I saw today that the Nobel Prize for Chemistry went to women, to a team. So a French scientist, Emmanuel Charpentier, totally butchered that name. My apologies. French is not my strong suit. And Jennifer A. Duanda, also butchered that. Very sorry for that. So I was just kind of, I thought it was really interesting that Nobel Peace Prize was awarded today, and I thought it tied in really well with your talk and the work you've been doing at the museum with these two collections items. So I'm wondering if these two women winning this prize, if that's a sign of change for the Nobel Peace Prize Committee, if we're going to see more women being nominated and winning the prize, and what you think the impact might be for the future of science with these two women winning such a very prestigious prize for their work in chemistry.
Yeah, absolutely. Well, I mean, for one, the recognition of women in science is long overdue, and so I think certainly today's winners, for their work on CRISPR, that really has been a transformative and really influential development. It's likely to continue to be for decades to come in terms of the use of genetic engineering in medical treatment, as well as all kinds of different applications, potentially in ecological adaptation and insect control. There's lots of possibilities. So it's certainly a well-earned prize. There's a long way to go for the Nobel Prizes to begin to more accurately reflect who has done science and whose science, and who has really contributed to science. And I think there's sort of two issues here, and one is that the process for awarding the Nobel Prize has been very insular and very fiercely contested, and so moving there's been a lot of public pressure from different directions to try and make sure that more women are nominated and that there's a better representation of who's involved in actually awarding the prize, right? So try and get a more fair and better distribution of prizes awarded. But there's also the deeper structural discrimination in terms of how women can become principal investigators, can become the leads on various kinds of projects that can then down the road lead to this sort of recognition. And so it's not just awarding more Nobel Prizes to women, but it's also making it possible for more women to have the resources that they need and the leadership roles and the to remove some of the barriers, the expectations that women are going to be doing the lion's share of reproductive labor, right? Or are primarily responsible for taking care of kids, especially when kids get sick, or as we've been seeing with the pandemic as well, right? So women having to kind of give up their careers or step back, and so we need to overcome some of those things, right? So the story of Libby Merrifield, I think, is really significant, and one of the things I was really excited to put in was this point that both Bruce Merrifield very much understood, but that Libby Merrifield also talks about, that because she was taking care of their kids, essentially raising 6 kids pretty much by herself, that made it possible for Bruce to spend evenings and weekends and very long hours in the lab doing this kind of scientific work.
Yeah, it definitely seems like there are a lot of one-sided sacrifices in order to kind of create these big scientific discoveries and big scientific changes. So it sounds like there's kind of a change needs to happen socially, right? Society, how we view women, how we view childcare and child rearing, versus careers and jobs and things like that. But it also seems kind of institutional. A lot of these colleges, a lot of these labs might need to restructure so that those opportunities exist for women, so that they have these leadership roles and they have these paths to be leaders, so that they can then potentially win the Super Bowl chemistry or physics, and win that Nobel Peace Prize. So it sounds like there's a lot that needs to change, and so I'm wondering kind of like where do we start with that change? Like, is this kind of the first step, like bringing these stories to life at the Science History Institute with these collections? Is that kind of the first step toward recognition that maybe people can then go forth and try to fight for these changes, and maybe we can start seeing some of those changes happen in college classrooms and then laboratories and then forward?
Well, that's certainly part of my hope, right? And so we're hoping to use programs like this, or sort of build college education programs, college classes around sort of sessions of particular classes around the storytelling in the museum, to help to reach out to different audiences, and to people who may not see themselves in the history of science, or in the sciences past, the way that it's often represented in, say, college textbooks, right? College science textbooks, things like that. So we're definitely, we do hope to engage underrepresented women, people of color, other groups of people that have been actively excluded from science, or actively marginalized from science, through these kinds of programs. But I think one of the things that we also want to do is we want to, history can show that women have been significant contributors to science. It's just that we've forgotten those stories, right? And so trying to recover those stories and resurface those and share those with audiences is an important part of activism, right? It's certainly not the only thing that's important, but it is one piece of the puzzle.
Yeah, absolutely. Wanting to make sure we're telling, the whole history in its truth, and making sure that people are engaging with that, I think, is a really important first step to make sure that things change in the future, and that maybe these stories don't get hidden or possibly erased going forward. We do have a really great question from Lisa Ruth Rand. So, hi, Lisa. She is very excited to see the immigration policy that's going to be part of the refresh. So you can see the questions up on the screen here. Can you share some ways that this will be conveyed in the exhibit design? She also mentioned this is very important given the recent changes to H-1B visas.
Yeah, absolutely. Yeah, so I would say in the exhibit design, we kind of are being, so we certainly show a picture of Yamashita working with the instrument. That the image I showed you there is one of the ones that's going to be printed on the reader rail, so people will actually kind of be able to, he'll be really sort of highlighted with that. I mentioned I'm kind of explicit that in writing the text that it's that immigration policies were relevant and promoted international exchange. I don't directly kind of address the contemporary policy explicitly in this exhibit, in part because things may change after the next election, for better or for worse. So we're kind of sticking to that historical story. But I think it is very relevant that people begin to understand that science, that good science, depends upon international exchange, and no country has a monopoly on outstanding scientific ideas. and so or outstanding scientific institutions, right? And that it is that process of exchange and moving between countries and talking to different people and being exposed to different ways of thinking about the world is really crucial to scientific advances, and then the kinds of technological and medical advances that may come from progress in basic research.
Yeah, no, that's great, Roger, and I think you can see a little bit of that with the current pandemic, and countries trying to work together to come up with a vaccine or some form of treatment, especially for our COVID long haulers, those who have had symptoms and have been dealing with COVID for months. There just doesn't seem to be an end. They're going to need prolonged treatment. We're going to see explosion of more disabilities coming after COVID, because I do believe there will be an after COVID. I don't know how long it'll take to get there, but you can see the international scientific community, starting with China, which faced this virus first, working with and supplying and even sending their own doctors and medical teams and scientists to some of these other countries to work together to battle this and figure out ways to protect human life and kind of lower the death number. So I think especially now it's really important to have those kind of international ties and those communities working together, because science, as you mentioned, happens in a lab, but with some of the images you showed, it's not one person. It's huge teams of people, and those teams are going to be made up of different people around the world. So I think that's a really great point for kind of people to keep an eye on now, especially that whatever happens with COVID, whatever is created, whatever we get vaccinated with at some point in the future, was worked on, created, studied, researched by multiple people from all over the world. So thank you for your question, Lisa. That was a really great question. Mm-hmm. Speaking of large groups working together in a lab, you mentioned how important grad students are to some of the work that's been done. But you also mentioned that it's very limited, the amount of people, the amount of names that can be put in for a Nobel Peace Prize. So I'm wondering, are there ways that grad students can be kind of included and mentioned in these discoveries? Should they? How do we go about that? Or is working in a lab at on what could be an important scientific discovery kind of equivalent to an unpaid internship, where you're just getting exposure and experience, but you're not really getting much else?
Well, I mean, the work that graduate students do in scientific laboratories is work, right? And they quite properly should be paid for that work. They are also scientists in training, but there are lots of kinds of places and occupations where we recognize that sort of training or journeymen and other kinds of steps along in an occupational process of learning towards becoming sort of a fully fledged or fully skilled worker. Those are things that need to be paid, and they are jobs also, right? So it's certainly, I think, it's important to recognize that is work, and although it is not the kind of work that is necessarily most prestigious or most highly rewarded, the kind of scientific work that's most prestigious or most highly rewarded, it is a kind of labor and needs to be compensated, right? And that's also crucial to diversifying who is a scientist, right? Paying people, you can't expect people to fund themselves for many years while they learn to be a scientist, or while they learn to be a historian as well, or a sociologist. That graduate school, those years in graduate school need to be compensated. Otherwise you simply end up with people, basically rich people, or people with whose families are willing to pay them and support them. And that becomes your next generation of scientists or professors or what have you. So that's that kind of work is really crucial. it's somewhat because so few people will ever win the Nobel Prize. It's probably more important to think of it in the much broader structural terms. For the people that are involved in these kinds of really prestigious research, it certainly, it was a thing that Yamashita references even today. If you check out his LinkedIn profile, which I did as part of the research for this, he references that he was part of Fens' lab, that doing research that was eventually that was recognized by the Nobel Prize. So that that can certainly be a career launcher. But again, that's one of the reasons that it's so important that we're careful about who and make sure to be inclusive about who actually is nominated and who actually wins these Nobel Prizes, because it really can be a launcher not just for not just for the person awarded, but for the people associated with that research.
Yeah, absolutely. It's just so interesting how many people and how much work goes into what these huge discoveries and wind up being, and some of the impacts they have. I think a lot of people have they think science is very kind of singular and it happens very quickly, and not that it's a huge team of people that can take years and years of research and failed experiments. Failed experiments are always very important in science because it teaches you what you did wrong and gives you ideas about what can change, and then you can go back to the drawing board and eventually find the right combination of things that works. So
I would say one of the things that I'm really excited about with the refresh is that it's a chance to set the scientific research that often when a Nobel Prize is awarded, it focuses the citations, and the discussion around it tends to be sort of quite focused on the scientist and the science itself, and maybe the instrument, and then perhaps the impact downstream from that discovery, right? So the role of protein, electrospray mass spectrometry, which could then enable people to identify proteins in samples, and contributes to the science of proteomics and the discovery of kinds of new drugs and better understandings of human physiology. And the stories usually kind of look downstream from there, but much less often does media coverage kind of look back upstream. So what were the changes, and what were the institutions, and what were the funding sources that made that science possible? So that's one of the things I really enjoyed in kind of bringing to this story, is to be able to say, actually, look, the history of cruise missiles is pretty relevant here. And although this is an exhibit about biochemistry, backyard volleyball games and cruise missiles and space newts are all part of this story. And in order to understand what really is behind a Nobel Prize, you need to look at it from these many different angles.
Yeah, it's something that I appreciate as a historian. I have 2 history degrees. I am not a scientist. I enjoyed science in school. I did very well dissecting animals. One of the few that wasn't grossed out by it. But science wasn't my path in life. So being able to look at more of the history surrounding it is something that I think is really important. And it makes me wonder if, these kinds of histories and these histories of science, even if it's just certain famous scientists or certain famous scientific discoveries, shouldn't be included in kind of your core curriculum, maybe starting in high school and getting into college, whether you're going to be a scientist or not, because having that kind of social and cultural knowledge, I think, is really helpful going forward. Even if science isn't going to be your path, at least you understand and can think critically and can research as to all the different parts that influence, these big decisions and these big discoveries. So that's my soapbox. We should include history with everything, right? STEAM, not STEM. Actually, recently some articles came out that highlighted the importance of history around science, and so that's when scientists leave and they're out in the world creating these wonderful things that are going to impact us for generations, hopefully positively. have that historical thinking behind it, so they can understand all the different pieces that have gone into it. I think it's really important that history is wrapped into science. So I'm really looking forward to some of the refresh and some of the changes. I know you work specifically on just the two collections items there, but in case anyone isn't aware, we're kind of refreshing more than just that one phase. So we'll get to see more of these stories being kind of unearthed and shared in other parts of the museum.
Yeah, there's some. I was as I was filming my things in the museum, I was able to have a look at a bunch of the new very colorful and very exciting, interesting graphics that are going in. So there's some wonderful work by well, a former colleague of ours, Jess Martucci, who's done some amazing things rethinking how we talk about insulin and the measurement of blood and counting of blood cells, and sort of thinking about the relationship between blood and disease over time. And so it's a really gorgeous and really rich with images and human stories about that. We've brought in, the kind of the molecular sciences can reach out and touch so many different aspects of the modern world, and so we're really kind of drawing together a lot of different stories that come in there. There's some wonderful exhibits on chemistry sets and how people have learned chemistry and the changing ways that people have learned about chemistry over time. But we also talk a lot about electricity, from the earliest batteries to the sort of the transformation of electrical society, society by telephones and telegraphs and electrical power in the later 19th century, all the way up through electronics. And one of the things that I'm really excited to have brought in is a Teddy Ruxpin doll, electronic bear, which actually has some very interesting connections to the history of recorded music, and as well as the defense industry, plus stories about rare earth elements and contemporary stories about pollution and environmental degradation. So there's a really wide range of stories that you can encounter when you come to the museum, and hopefully we'll be able to open again soon. There's not a particular we don't have a sure date yet, but definitely do check back in the spring in the hope that we'll be able to open, pandemic willing.
Yeah, absolutely. And I think this is a really great introduction to some of those changes and some of those stories to get our audiences excited. For me personally, I think this is kind of a really great avenue for museums to take. How do we make those historical changes? How do we make sure these histories aren't erased? How do we share and inspire our visitors and future generations of scientists or historians of science? And I think what we're doing at the Science History Institute with this makeover, right, or this refresh, I think is a really great first step, and is where kind of museums can anchor what's currently happening, what's happened in the past, and how those are going to influence the future. So for me, it's really important that museums kind of take those stories and highlight them and share them with people. And I'm so happy to see that we're doing that. So definitely, please, everyone, whenever it is safe and when we are open, come down to Philly, 315 Chestnut Street, and check us out, because it's going to be awesome. So thank you so much, Roger. Thank you for joining us. Thank you for being our first in this fall's lunchtime lecture series. I hope you had as much fun as we did, and I'm really looking forward to seeing the work that you've done in the museum. So thank you so much.
Well, thank you so much, and I look forward to hearing the talks in coming weeks.
Awesome. So thank you everyone for joining us, even with our technical difficulties. I hope you were able to enjoy Roger's talk. And like Roger mentioned, we do have many more lunchtime lecture speakers coming up. Our next one is going to be next week, Wednesday, October 14th at 1 p.m. We are going to hear from Gustav Lester, PhD candidate, History of Science at Harvard University, as well as a pre-doctoral fellow in early American history at the American Philosophical Society. And he will be talking about geology and settler colonialism, so very on-brand topic. So please make sure you check us out then. It'll be another live stream on YouTube, and I promise our chat feature will be fixed by then. Make sure you follow us on all our social media channels. You can find us at SciHistory.org, Twitter, Facebook, YouTube, and Instagram. And that'll help you learn more about our upcoming events, as well as other programs and things like that we're hosting. And if you enjoyed today's program and you would like to support the Science History Institute's mission to preserve and celebrate our scientific and technological culture through storytelling, as Roger mentioned, it's very, very important for us to share these stories. So if you support that and want to hear more, you can donate at www.sciencehistory.org/support our mission. So thank you again for joining us, everyone, and have a wonderful day. Happy Wednesday.